In this section, we're talking about quadratic relations. So this is an introduction to quadratic relations, what they look like, and some of the key features of quadratic relations. So here I have a graph. The x and y axes are here. And then here is the graph of the quadratic itself. And then these dashed lines highlight some of the key features along with the circled and numbered points. So, quadratic relation has a general formula of y equals ax squared plus bx plus c. A, b, and c are all real numbers. That's what this means. They belong to the set of real numbers. Just a short form of writing that. That means they're whole numbers, they're integers, they're fractions, they're decimals, they're any number that you may have dealt with. There are some numbers that they don't fit, but we will get to those in another unit. This shape here, this symmetrical U shape, is called a parabola. And by symmetrical, I mean that it is the same on either side. So if I take this ruler here and line it up, it's a mirror image of itself on either side of that line. So that dashed line I'm using here, it's a mirror image of that. If you recall back in elementary school, you may have used a red mirror that you put on a line and it would make a mirror image of the item on the other side. That was the symmetrical object. That's what we're doing here. If we put the mirror on here, this red line, it would flip and mirror itself on either side. So the parabola is the symmetrical U-shaped graph of the quadratic relation. It might open down like this, or it may also open upwards like this. It just depends on the equation. It will never open sideways. It'll always be either directly up or directly down. The point, so that's point number one. Point number two is right here where you see the graphs going up and then it changes and starts going back down. If it was opening upwards, it would be coming down and then change and go back up. It would be that point where it's changing. That point where the graph or the parabola changes direction is called the vertex. So when we're talking about the vertex, we're talking about the point where it changes direction. It is the maximum or minimum value of the parabola. And so in this case here, it's the highest point on the parabola. The parabola would continue down forever, so there is no minimum point in terms of that. It's an infinite value. But there is a maximum point that stops here at 1, 2, 3, 4. So it stops at a height of 4. Again, if the graph opened the opposite way and was opening upwards, then that upwards graph would have a minimum value or the lowest possible value of the vertex, and then it would continue upwards infinitely. Some other key points. You should be familiar with the concept of where the graph crosses the x-axis. It's called the zeros, roots, or x-intercepts. You should be familiar with x-intercepts from linear equations. We also use the term interchangeably zeros and roots. That'll make more sense again as we move forward in our quadratics units. Do note with a quadratic, there may be 2 points, like this example here. The graph may also have 1 point if it was to, say, go up. I messed that up. Hold on. If it goes up and just touches the line like that, it could just have one single intercept or zero. Or it could be like the one I was drawing earlier up here, lightly. It could be like this, where it never touches the x-intercept and thus has 0. So our parabolas may have 0, 1, or 2 zeros. The axis of symmetry is the line that divides the parabola into its symmetrical parts. That vertical line that divides it into its symmetrical parts. That's this line right here. It goes through the vertex. Always goes through the vertex. And we'll divide the graph evenly into 2 halves that are mirror images of each other. And it has an equation of x equals, and then whatever the x coordinate of the vertex is. So in this case here, my vertex here is at -1. So this would be x equals -1 for the equation of this line. Again, any vertical line on a graph will have the equation x equals whatever x value it goes through. In this case, it's going through -1. And then finally, the other key, and kind of connects back to the vertex, is that maximum or minimum value, the highest or lowest y value of the parabola. So it just takes the y value of the vertex. So if we look at this one here, again, that's the y value of the vertex is going to be 1, 2, 3, 4. So it is a maximum value at 4. It's maximum because it's the highest point. Again, if the graph opened the other way and opened upwards, then it would be the minimum point. One other concept to take a look at is the finite differences. So you may recall working with first differences last year in your grade 9 courses. They are a type of finite differences. When we calculated those, we found that if the first differences were the same, then the graph was linear. Otherwise, it was nonlinear. Now we're going to look for the second differences in this. And for those of you who are not recalling that, we're going to make a table of values and then calculate these differences. So in this case here, we're going to find the second differences for the equation y equals x squared plus 2x plus 3. So I have the equation up here, and how I would calculate my table of values, I'm going to plop these numbers that I picked. I picked -2, -1, 0, 1, 2, and 3 as my x values, and I'm going to just plug them in for the x here. So I will have -2 squared. Notice I'm putting it in brackets. If it's not in brackets and you type that in your calculator, you will get an incorrect answer. -2 plus 3. And I have -1 squared plus 2 times -1 plus 3. 0 squared plus 2 times 0 plus 3. 1 squared plus 2 times 1 plus 3. So I'm just plugging in the x value in for the x value here. It's no different than making a table of values for a linear graph. And then we're going to calculate all these. So we need to calculate all these now. So we have 4 minus 4 plus 3. So that is 3. 1 minus 2 plus 3. So that's going to give me, 1 minus 2. So -1 plus 3 is going to give me 2. 0 plus 2 plus 3. That's going to give me 3. 1 plus 2 plus 3, that's going to give me 6. 4 plus 4 plus 3, that's going to give me 11. And then 3, so it's 9 plus 6 plus 3, that's going to give me 18. So there's my values, 3, 2, 3, 6, 11, and 18. And then to find the first differences, you just look, what's the difference to go from 3 to 2? So to go from 3 to 2, we're going up by, or we're going down by 1, so that's a -1. From 2 to 3 is a +1. 3 to 6 is a +3. From 6 to 11 is a +5. And then from 11 to 18 is a +7. So we get -1, 1, 3, 5, and 7. That there is our first differences. We took the difference of the y values. And they're all different, which means it's not linear. But if we go and take the second differences, from -1 to +1, we're going up by 2. If we go from 1 to 3, we're going up by 2. If we go from 3 to 5, as well, we're going up by 2, and from 5 to 7, we're going up by 2. These here are the second differences. So those are the second differences. They're all the same. Thus, we know from the table that this would be a quadratic equation. Again, we know because x squared is the highest power of x. There's no x cubed. There's no x to the 4. We have an x squared here as our highest power. And we have second differences that are constant. So again, make sure you know the different portions of the graph. Be able to look at the graph and label those portions. The vertex, the x or intercepts, roots or zeros, the axis of symmetry, the parabola itself, and then the the maximum or minimum value. You should recognize the formula with the x squared. Has to have an x squared in it. If it doesn't have an x squared, then it is not going to be a quadratic. And then the a, b, and c values need to be along to the real numbers. They have to be real numbers.